So it's section 11.5. Okay, and the argument is going to be what is alternating series. Alternating series, going to be very important series for the rest of the course, and very easy series. Okay, so what is going to be alternating series? We are going to consider, you see, it's going to be a series. Let's just give you an idea. It's going to be a series whose terms are going to be alternating in positive or negative. And alternating, okay, alternating series is going to be a series whose terms are going to be alternating the positive and negative, or the other way around, positive and negative. Okay, so this is how we're going to denote it. So if we go with the Bn for this group, if Bn is a sequence of positive numbers, is going to be positive numbers. Okay, then this series, then you may have a sequence of a sigma of, you see, sigma of -1 to the n minus 1, Bn, and from 1 to infinity. If you replace n by 1, so 1 minus 1 would be 0, so that it would be 1. If you replace n by 2, so 2 minus 1 would be 1, -1 to the 1 would be negative, B2. And you replace n by 3, 3 minus 1 would be 2, -1 squared would be positive. So that gives B3. You see, alternatingly, it's going to be positive, negative, positive, negative. Just keep going up. Okay, it may be the other way around. Okay, or you see, or if you like, you see, you may start with a -1 to the n, this b to the n from 1 to infinity. In this case, when you replace n by 1, so that you have negative b1. It's going to be negative b1 plus b2 minus b3 plus b4, etc. Okay, so we usually focus on the first one, but it's the same thing. So as you can see, the terms positive, negative, positive, negative, negative, positive, negative, positive, forever. So that would be okay, alternating series. Okay, there is going to be a very easy test to check if this series is going to be convergent. We call it alternating series test. And that test would have, if this series is given to you, look at this Bn, this sequence. You check to see if this Bn is decreasing. Decreasing means as you go on, B1, B2, B3, B4, the terms of the sequence getting smaller and smaller and smaller. It's going down. And the second condition is if this limit of the Bn, general term, when n goes to infinity is 0. If these two conditions satisfy, your series is convergent. Otherwise, it's going to be divergent. It's a very easy test. Okay, you have to go know the name. We call it the alternating. Okay, so that's going to be alternating. Remember, you cannot use the previous test because the previous test can be used only if the term of the series are all positive numbers. They are not. alternating, you get a positive, negative, positive, negative. So that's why you have to use this series. We call it alternating series test. Alternating series test, or AST. Very easy test. And this is going to be the case that if a series is given to you, okay, so suppose sigma of -1 to the n minus 1 bn n from 1 to infinity is, okay, is an alternating series such that two conditions hold or satisfy, such that the first condition is going to be, you see, the first condition is that this sequence Bn must be decreasing, is decreasing. You have to prove it, that's decreasing. Okay, it's going to be decreasing. Decreasing means if you get the first term, you see the first term is going to be bigger than the second term. So that gives you bigger than the third term, etc. So as you go on, the term of the sequence getting smaller and smaller. B1 is the bigger one. Okay, so this is going to be the one, or in general, sometimes they write Bn plus 1 is less than equal to the Bn. So this means if the index is higher, the terms of the sequence is going to be, okay, smaller. But basically, as you go on, the term of the sequence getting smaller and smaller. So this is the first condition. The second condition, of course, is the limit of Bn when n goes to infinity must be 0. Remember that was the part of all the other series as well. If this sequence, if this limit is not 0, so the series is divergent. It's the same thing for this one. So if these two conditions satisfy, then simply the alternating series, okay, sigma of -1 to the n minus 1 Bn, n from 1 to infinity is convergent, is going to be convergent, and you're done. Very, very easy test, to check when the question would be given. Okay, so it's easy to identify its alternating series because it's going to be positive, negative, and you just check these two conditions and then you're done. Okay, it's some example. The first one is the most popular example that we have. We are going to use this one quite a lot. Remember harmonic series that we talked about it? Harmonic series was 1 plus 1/2 plus 1/3, etc. Sigma of 1 over n. That was harmonic series, and you know that that was a p series with p equal to 1, and the series was divergent. We have similar one, harmonic alternating harmonic series, which is very popular. Okay, so this is going to be the case. You see the alternating harmonic series. Okay, is this one. Is sigma of -1 to the n or n minus 1 divided by n from 1 to infinity. So if you replace n by 1, you see the top would be a positive 1, the bottom one would be 1. So your first term would be 1. Then your next term is going to be 1/2. Then you get a 1/3. You see minus a quarter, etc. If you don't have -1 to the n sigma of 1 over n, you know that it's a harmonic series, and harmonic series is divergent. But this one, we are going to show that this is convergent. You see, note that in this case, note that as we go in this, if you want to go back to that theorem, your Bn is equal to the 1 over n. Okay, 1 over n for n equal to the 1, 2, 3, etc. If this is going to be the case, then you know both conditions. You have to check it, or you have to express those conditions on the test. Okay, the first one, you can see that the first term is 1, 1/2, 1/3, a quarter, etc. So the term of this sequence going down, down, down. As the n increases, 1 over n is going to be smaller and smaller. So the first thing you are going to tell us that the Bn, okay, Bn is decreasing, because the first term is 1, which is bigger than 1/2. 1/2 bigger than 1/3, 1/3 a quarter, etc. So that's decreasing, okay? And the second condition was the limit of the Bn. Limit of the Bn, when n goes to infinity, your Bn is simply sigma of 1 over n. Sorry, 1 over n. N goes to infinity, that would be 0. You see both conditions satisfied. The first condition that the Bn must be decreasing. The second condition that the limit of the Bn n goes to infinity must be 0. So this means the alternating series, sigma of -1 to the n minus 1 over n, okay, is convergent. So that would be very interesting that the harmonic series by itself is divergent, but alternating harmonic series is convergent. Okay, remember this one, and it's going to be used quite a lot. Now, this proof is very nice to prove this series, but if it was a face-to-face, I usually prove it, but you know, we don't need it. So let's check another one to see what else do you need to do in order to get this series. Your problem is going to be this decreasing one that you have to show us. That was clear, but you have a technique of, because remember the sequence is a function. So sometimes you may have to use the derivative to prove that this is decreasing. So that's going to be example number 2. Okay, example number 2, we want to check if the series is convergent. Okay, determine if the series, the alternating series converges, okay, converges or diverges. Converges or diverges. Okay, so let's check this one first, sigma of. So the first one is this one, sigma of -1 to n, but your sequence is 2n over 4n squared plus 1. You see this one? And of course, when n goes from 1 to infinity. Again, you want to check to see if this is going to be convergent or divergent. Quickly, you look at this limit first. You see the limit of the 2n over 4n plus 1. You know that if you're showing it, the degree of the bottom is higher. So this limit is 0. Check that one first. Then, of course, you have to prove that this is going to be decreasing. Okay, so the solution is going to be, you know that it's going to be alternating series. So you have to explain it. You suppose that your Bn is going to be equal to the 2n over 4n plus 1. Okay, so I will check the limit first. Okay, if this is going to be not for n equal to the 1, 2, 3, etc. So you claim that you can call it number 1, that the limit of the Bn goes to infinity. Check this one first, because if this is going to be non-zero, your series is divergent. Okay, it's going to be 4n over n squared. You know that you can shrink the top, it's going to be 2n, and the bottom one would be 4n squared, or just you can say that the Since the power of the bottom is higher, this limit is 0, we accept it. But if you simplify it, so that give you 1 on the top, 2n down the bottom. N goes to infinity, you know that that's going to be pizza problem. It's going to be 0. Because there is n on the denominator. When n goes to infinity, denominator would be infinity. So the first condition, that condition satisfied, the limit of Pn is 0. The second one that you have to prove that this is going to be decreasing. You see, the other one was clear, but not this one. So what you can do for this type of problem is you can call it f of x. Remember, I want to, you know that if the derivative of the function is negative, that function is decreasing. So you can use that fact. But we already talked about it. If you stay with the n, you cannot differentiate it. Because, n is 1, 2, 3, 4, 5, 6 is the discrete. So you check it to the f of x so that your domain would be all real numbers, and then you differentiate it. Okay, so be prepared for it because this is not clear. So introduce f of x equal to the 2x over 4x squared plus 1. Differentiate it. Quotient rule. Derivative of the top times bottom, bottom top. Derivative of the top would be 2 times bottom, 4x squared plus 1. Minus derivative of the bottom is going to be 8x times the top one, 2x. Okay, divided by the bottom squared, 4x squared plus 1 all squared. Okay, stay on the top, simplify it. Distribute that one, that give you 8x squared plus 2, and that would be minus 16x squared. That would be divided by 4x squared plus 1 all squared. Okay, go on, combine the like terms. So f prime of x is going to be, the bottom one is 4x squared plus 1 all squared. And the top, when you simplify it, that give you what? 8 minus 16 would be negative 8x squared. Okay, plus 2. See? You see this, this bottom one is always positive. It's going to be always positive, but the top one is going to be something like, because x is very big number. Remember, x is just the n. It's going to the infinity. So you can forget about these two. The top is negative 8x squared is always negative. Or you can pick x, it doesn't matter if you just pick x equal to 1, because x is going to be this one. If you put x equal to 1, that gives you negative 8 plus 6, which is a negative 6, is negative. Then x equal to 2, 3, 4, 5, 6. So this is going to be negative for all x which are going to be greater than or equal to 1, if you like. Okay, so this means that sequence, when the derivative is negative, so the function is going to be what? The function is going to be decreasing. So f is going to be decreasing, and take you back to the fact that your sequence is, so the sequence Bn, if you like, Bn is decreasing. Okay, so be ready for it. Sometimes you may have to use the derivative to check it, because this is not clear, okay, not like the previous one. So basically what we did, we just proved those two conditions. So the sigma of negative 1 to the n over 2n over 4n squared plus 1 is convergent. We're going to give another method later, but this is easy method, okay? It's convergent. And we're done. Okay, so you have to check both conditions. The condition that the limit of the general term is 0, and the condition that this is decreasing. The previous one was easy, but not this one. It's not clear. So you differentiate it. You prove the derivative. You say we use the quotient rule here. The top is a square, it's always positive. The top one is a negative 8x squared plus 2. You can forget about the 2 really. Or x start from 1. You see, if you put the 1, negative 8 plus 2 would be negative 6. Then x equal to 2, negative 16 plus 2. So it's always negative at the top. So your sequence is decreasing and the limit of the general term is okay, is 0. So in that case, the series is convergent. Okay. So I give another one so that you see when this is going to be divergent. Look at this one. Limit of -1 to the n. You may be given n over n plus 1. You see when n goes from 1 to infinity. Again, this is alternating series. Your Bn is n over n plus 1. If you take the limit of n over n plus 1, you know that. You shrink it, you see that would be n over n. The limit would be 1, which is not 0. Since the limit of the general term is not 0, this series is divergent and Newton. Okay, so the solution is going to be, you put the Bn, you say that this is, it is, okay, and alternating series. Alternating series with what? With the Bn, which is equal to the n over n plus 1. Quickly check the limits. So the limit of the Bn when n goes to infinity is the same as the limit of the n over n plus 1 when n goes to infinity, and that would be the limit of the n over n when you shrink it, which is 1, is not equal to the 0. You know that if the limit of the general term is not 0, the series is divergent. Okay, so the series diverges. And then you are not going to continue to get this one. Okay, so this is going to be the case for the alternating series. Very easy test, very easy to check, you know, this type of test. Okay, so what we did so far, what we have, if the term of the series are all positive, we can use all the tests that we talk about, the integral test, limit comparison test, okay, we talk about the p-series, all those conditions, ratio tests, remember root tests, all of them can be used when it's positive. But if it's not going to be positive, you may get this one. You see, it's alternating positive, negative, positive, negative. You just keep going. So what else? What are you going to do if some of the terms are positive? It's not like this one, nice, positive, negative, positive, negative. So what are you going to do if you get a series that some of the terms of the series are positive, some of them are negative, but they are not nicely organized? So what are you going to do about it? So what we're going to do, we are going to introduce a new notation. That notation is going to be called absolute convergent. You see, our difficulty is that whether the term of the series are going to be positive or not, like this one. So what we're going to do is we are going to introduce a new convergence. That new convergence is, if you, instead of this series, you just consider the series with the absolute value. If you put the absolute value around this series, you see that -1 to the n will disappear. So you changed your series to the series of positive terms. If it's going to be positive terms, you can use all the previous theorems that we talked about it to check whether this resulted series is convergent or divergent. But since we use the absolute value, in this case, we say this series is absolutely convergent. Okay, so that's a notation of it's very, make things so easy for us. So we always go with the absolute value. If it's going to be absolutely convergent, automatically it's also convergent. Okay, let's give you the definition. It's a very interesting definition. And when we go to the rest of the book, okay, rest of the course in calculus, we usually go with the absolute convergent because you are going to see the power series starting next week. And in the case of the power series, there's going to be an x involved. And since we don't know whether x is going to be positive or negative, we use the absolute value. So we need this one for the rest of the course. Okay, so that would be 11.6. This would give you the last terms of the convergence series, and when we're done, then we can start with the kind of function type. Okay, so what is this? We are going to introduce to you what is absolute convergence. Absolute convergence. What is absolute convergence? Okay, that's going to be the one. Now, a series is going to be, give you the definition. A series, now you are not going to worry about whether the terms are going to be series going to be positive or negative. You can use this one all the time. A series, pay attention to the definition. A series, sigma of an, a given series, whatever an is going to be called, is called absolutely convergent. Okay, it's called absolutely convergent. Okay, we're going to call it absolutely convergent. Absolutely convergent if this series, if the series sigma of absolute value of an is convergent, is convergent. Okay, so if you take the absolute value around it, when you take the absolute value, then you can use any of those previous theorem that we talked about it. If you put the absolute value around it, and the result is going to be a convergent series, you go back and you claim that the original series is absolutely convergent. Okay, so give you an example. Let's see what's going on. Look at this one. Okay, look at this series. Consider, okay, consider this series, sigma r -1 to the n minus 1 over n cubed. You see, this is alternating series, and we already give you a method to check the convergence of this one. But we want to know if it is absolutely convergent. So if this is going to be the series, then what you're going to do is you are going to consider the absolute value of this series. Note that. You see, if you consider the sigma r, absolute value of -1 to the n minus 1 over n cubed. Absolute value would take care of those negative sign. So that -1 to the n minus 1 would disappear, would be 1. Because you can take the absolute value on the top and on the bottom. Down the bottom, n is positive. So we get the n cube again. You see, it's going to be the 1. That gives us sigma r. The bottom one would be n cubed. But the top one, the absolute value of a top, absolute value of -1 to raise to any power you like, would be 1 over n cube. Would be 1. Okay, the absolute value of -1 to the n minus 1 would be 1. And the absolute value of n cube would be. But what is this series? You know that this is a p series. Is a p series, p equal to the 3 greater than 1, so it's convergent. So the series of the absolute value is convergent. So the original series is absolutely convergent. Okay, so is a p series. A p series with p bigger than 3, and it's convergent. And is convergent. So this means the original series. So your original series, sigma of -1 to the n minus 1 over n cubed is absolutely convergent. Absolutely convergent. You see, very nice one. So we take absolute value around it, it's going to be absolutely convergent. You are going to see in a minute that if the series is absolutely convergent, that series is convergent too. So this series is also convergent. You see, easy method. You can check it with the alternating series, but this method is much easier. Okay, so that's going to be one example. So it's going to be absolutely convergent if you can work on the absolute value. Give you another one, then we give you a new definition. Consider the alternating harmonic series, okay? Consider the alternating okay, harmonic series. Remember, alternating harmonic series is this one, the 1 minus 1, 1/2 plus 1/3, etc. So it's a sigma of -1 to the n minus 1 over n. You know that it's going to be -1/2, 1/3, etc. Okay, and we already talked about it. This is convergent. Okay, consider the alternating harmonic series. We know that it converges. It is a convergent series. We already talked about it. Because the Bn is 1 over n is decreasing and the limit is 0. But look at this one. How about the absolute value around it? But if you take the absolute value of a -1 to the n minus 1 over n, we talk about the absolute value on the top. Make this one into 1, and the absolute value of bottom one would be n. But you know that sigma of 1 over n is divergent. It's a P series with P is equal to 1, or is a harmonic series. So this is divergent. Okay, so this means the original series is not absolutely convergent. Okay, so this means, so sigma of, okay, sigma of -1 to the n minus 1 over n is not absolutely convergent. Absolutely convergent. Okay, if you get this situation that the series is convergent, but it is not absolutely convergent, we have a name for it. We say that the series is conditionally convergent. Okay, conditionally convergent. This is going to be another expression, new one. So we get absolutely convergent, convergent, conditionally convergent, and divergent. Okay, so give a definition. What's going to be a definition of a conditionally convergent? There you are. A series. You see, a series sigma of an is called conditionally convergent. Conditionally convergent if two conditions satisfied. If the series is convergent, if sigma an is convergent, but not absolutely convergent, but sigma of an, absolute value of an is not, is divergent. Okay, is divergent. Okay, or if you like, or sigma an converges, but not absolutely convergent. Absolutely. Okay, converges. So in that case, the series is called conditionally. Okay, conditionally convergent. So basically, give you this theorem that if the series is absolutely convergent, it's automatically convergent. This would be very helpful. You see, it's clear. The theorem is going to be if sigma of an is absolutely convergent, okay, absolutely convergent, it automatically is convergent to, then it converges. Okay, then sigma in is convergent. It's clear because when it's absolutely convergent, the series must be convergent too. So that will help you. So this means if you have any doubt about it, you just put the absolute value around this one. If this is going to be convergent, the original one is also convergent. If you put the absolute value around it, you get a divergent series. Okay, just go back, check to see if you can prove it's convergent using some other methods. So in that case, you are going to have conditionally convergent. Okay, for the rest of the course, we use just the absolutely convergent, but for the time being, we need to be able, to take care of this. And I give you an example to see how we're going to handle this type of problems. Okay, and you have at least one question on the quiz is related to this one, and I just give you the one from the practice one as an example. Let's check one first. So this is going to be the situation we're going to have. So we are going to ask you determine. Okay, if you see this type of ideas, you go for the absolutely convergent. But otherwise, all the other tests are going to be used. Okay, remember the other tests can be used if the series would have positive terms only. So we want to determine whether the series, okay, the series is going to be the series absolutely convergent, conditionally convergent, or divergent. Okay, so determine whether the series, let's say, are absolutely convergent, conditionally convergent, or just divergent. I say this is how you are going to be questioned. Okay, let's take the first one. You see, the first one is going to be kind of alternating one, sigma negative to the n, and this is going to be n squared, n from 1 to infinity. First thing to do, go for the absolute value first, always. Because if it's going to be convergent, it's absolutely convergent, and then you're done. So the solution is going to be, you take the sigma of the negative 1 to the n over n squared, the absolute value. You put the absolute value on the top, you will lose the negative sign, you lose the absolute value on the bottom, n squared. You know it's a p-series. Is a convergent p-series. P-series, you know that with p equal to 2, which is bigger than 1. That's it. You put the absolute value around it, it's convergent. So the original series, sigma of negative 1 to the n over n squared is absolutely convergent. Okay, absolutely convergent. And you're done. Okay, so we take the absolute value around it first, absolute value. When you put the absolute value around it, it's going to be a convergent series. Since you work with the absolute value, so the series is absolutely convergent. You know that when it's absolutely convergent, it's also convergent because you prove something extra. Okay, that's case one. Case two, check this one. -1 to the n minus 1 over radical n from 1 to infinity. Again, put the absolute value around it. Solution. So we take the sigma of the absolute value of -1 to the n minus 1 over radical n. Okay, the absolute value would take care of that sign and give 1 over radical n. You know that's sigma of 1 over n to the half. It's a p series. P is 1/2. Less than 1 is divergent. Is a divergent p series. P series with p equal to the half, which is less than 1. You see, when it's a divergent, this means this series is not absolutely convergent. Okay, so the series is not, absolutely convergent. Absolutely convergent. The question is it conditionally convergent? For the conditionally, you have to check the series at the beginning to see if the series by itself is convergent. If the series is convergent, but it's not absolutely convergent, so we say it's conditionally convergent. But look at the series. What type of series is this one? It's alternating series. Bn is 1 over radical n, and it satisfies those two conditions. Say, oh, bet. So you're not done because you have the option of the conditional convergence. So you have to prove it. You say, oh, bet this series, sigma of -1 to the n minus 1 over radical n is what? Is an alternating series. Alternating series with what? With Bn equal to the 1 over radical n. Okay, but you show that the limit of the Bn, n goes to infinity, when it's going to be limit of 1 over radical n goes to infinity. There is a pizza on the top, infinity down the bottom. This is 0. And this sequence is decreasing. You have to tell us two conditions. Remember, two conditions. The first condition is the limit is 0. And the second condition is the fact that the Bn is decreasing. Bn is decreasing. Decreasing because it's 1 over radical n, you see. Replace by n by 1, that give you 1. Then 1 over radical 2, radical 3, radical 3. So it's going to be, so we get these two conditions. So therefore, the series -1 to the n minus 1 over radical n converges. So what we have? We have the fact that the series is convergent, but it is not absolutely convergent. So this means the conclusion is going to be, so the sigma of -1 to the n or n minus 1 over radical n is conditionally convergent. Conditionally convergent. So conditionally convergent means the series is convergent, but it's not absolutely convergent. Okay, because when you put the absolute value around it, you arrive at what? You arrive at the p series, p equal to the 1/2, which is less than 1. It's divergent. So the series is not absolutely convergent. You cannot say that it's conditional convergent. No, you have to go back and check. You check the series, you find some other method to do it. The other method is just alternating series. So it's alternating series. The Bn is 1 over radical n. The limit of the Bn is 0 and the Bn is decreasing. So this series by itself is convergent. It's not absolutely convergent. So it must be what? It must be conditionally convergent to get these numbers, okay? So that make it quite, quite interesting case. So that's a number one, number two, and of course the third case is this one. Okay, the third case, we already talked about the third case, but I just write it down again so that you know it. So that is going to be sigma of -1. Okay, -1 to the n. I just repeat something like that. It's a 2n over n plus 1. You see, that's going to be the case. You know that this the general term, the limit is 2 is not 0, so this series is divergent. You don't have to check anything else, even if you put the absolute value around that. But just check this limit. Okay, for this one, the limit of 2n over n plus 1, n goes to infinity is 2, and the 2 is not 0, so the series diverges. Okay, the series diverges, and you're done. Okay, so these are going to be the cases that you are going to have with these alternating series and the absolutely convergent. Absolutely convergent, divergent make it easy for us for the rest of the course when we're dealing with the functions. And when we have the x, we don't know whether x is positive number or negative number. So it would be, we prefer to use the absolute value. So we work with the absolutely convergent for the rest of the course. Because when it's absolutely convergent, as we talk about it, automatically, it would be also convergent, okay? So that is why we work with this type of ideas. So let's go to that practice test. We have a couple of nice one. Number 6 is the one that I talk about it. The other part is just from the previous part that we did. Okay, so is number 6. Okay, so this is going to be, just go to the next page and explain it. Okay, I extend that your quiz is due on Tuesday. I extend it up to the Wednesday, Thursday, so that you get enough time, to prepare for it, because we want to make sure you know it, how to do it. Okay, so I do that one later tonight. So let's get that practice quiz number 3. It's a very good one for your next test. Okay, so I just graded your quiz number 2 as well, so you should have all your points so far. If it's anything missing, just let me know. Email me, then I'll check it. Okay, so this is question number 6 on this practice quiz number 3. It's the same thing. You want to determine, okay, we want to determine whether the series, okay, whether the series, and you have one question on that your quiz. The series is absolutely, it's very similar that you have. Okay, it's going to be absolutely convergent. Okay, absolutely convergent, conditionally. Okay, conditionally convergent. Or simply it's divergent. There are 3 cases and you have 3 on your quiz. Okay, let's check the first one, part 1. Part 1, the series is sigma of -1 to the n. Okay, and this is 1 over n cube root of n. N, of course, from 1 to infinity. Okay, so as we talk about it, the first thing to do, you put the absolute value around that. If you arrive at a convergent series, then you're done. Okay, so this is the case. So put the absolute value around it. So the solution is going to be, this is going to be solution. So we check the sigma of the absolute value of a negative 1 to the n, 1 over n cube root of n. Absolute value, take care of that negative 1, okay, negative 1 to the n. Just try to see if we can get a focus, a better focus for this one. Okay, if you go back, we should get a better one. Yeah, that's better. Okay, if you put the absolute value around it, when we don't write anything between n to 1 to infinity, you can do the same thing. So that negative 1 would disappear unless the rest are all positives. 1 over n cube root of n. You know that cube root of n would be n to the third. So that gives a sigma of 1 over n times n to 1/3 or third. 1 plus 1/3 would be 4/3. So it's going to be sigma of 1 over n to the 4/3. You know that this is a p series. Is a p series, p is 4/3. It's bigger than 1. It's convergent. So is a convergent. Is a convergent. Okay, p series. Convergent p series with p equal to the 4/3, which is bigger than 1. You have to explain it for us. There you are. You see, you put the absolute value around your series. The result is a convergent series. So the original series is absolutely convergent because we use the absolute value. Okay, so the given series, if you like, or you repeat it, you just say given series. So the series n cube root of n is absolutely convergent because we put the absolute value and we prove it for you. Convergent. Okay, so that's going to be your first action. You put the absolute value around it. Okay, that's the first one. Okay, so let's check another one. That was part 1. So the part B. Your part B is sigma of negative 1 to the n. Okay, negative 1 to the n. And this is going to be n plus 2. N plus 2 over n squared plus 3n. We check this one. Okay. So again, put the absolute value around it. So the solution is going to be sigma of absolute value of negative 1 to the n, and this is going to be n plus 2 over n squared plus 3n. Okay, and you remove the absolute value, the leftover is going to be n plus 2, and this is going to be n squared plus 3n. That would be resulted series. Now we're going to check this one. You have to shrink it and use the limit comparison test to check it. You know that if you shrink it, we already talked about this type of proof. So if you shrink it, it's going to be like the sigma of the n plus 1 would be shrinking to the n, and the n squared plus 3n would be shrink to the leading term, which is n squared. So the n would be cancelled out. So this would be like a sigma of 1 over n. And we accept this type of ideas. It's kind of a limit comparison test that we accepted for these type of problems. So this series would behave like sigma of 1 over n. We know that it's a divergent p series or harmonic series is a divergent. Okay, divergent p series. You know that we p equal to 1. So this means this series is not absolutely convergent. Okay, so the given series, if you like, the given series so far is not absolutely convergent. Absolutely convergent. So you're not done. You are going to check to see if it's conditionally convergent. For the conditionally convergent, you have to take the series itself. Okay, so the question that you have to answer, is it conditionally convergent? Conditionally convergent. So you have to check the series by itself. It's alternating series. You work on the Vn. So you say that, oh, sigma of negative. You have work to do for when if it's going to be this case. You see, you say that, oh, this is an alternating series. It's an alternating series with Bn. Bn of what? Bn of n plus 2 over n squared plus 3n. Again, you have to show that this limit is 0, which is clear. You see, the limit of the Bn when n goes to infinity is going to be 0 because you know that you shrink it, you get 1 over n. Or the degree of the bottom is higher. So it's going to be limit of n squared plus 2 over n squared plus 3. N goes to infinity if you shrink the top and the bottom, or just say that since the degree of the bottom is higher, this limit is 0. It's going to be n over n squared. N goes to infinity, so it's a limit of 1 over n. N goes to infinity, so that's 0. Because this sequence is like the b 1 over n. And the bn is decreasing. You don't have to prove it because it's like 1 over n. So we can say that the bn is decreasing. Again, we accept it because we shrink it and we see it. So you see two conditions of the alternating series satisfy. The bn is 0 and the bn is decreasing. So this series, alternating series, is convergent. So the series is convergent, but it's not absolutely convergent. Therefore, it is conditionally convergent. Okay, so it takes time, but it's a nice, very nice one. So if we continue, we say that, so the alternating series. Okay, so the alternating series, the given series, or the given series, I just repeat it because it's a new page. You see that was the case that we have n plus 2 over n squared plus, okay, n plus 2, n squared plus 3 is convergent. Okay, is convergent. So the series is convergent, but it's not absolute convergent. So the conclusion is going to be, therefore, the given series is what? Is conditionally convergent. Conditionally convergent. You see, this is the case there to prove the series is going to be conditionally convergent. Absolutely convergent is, that's why you go with the absolute value first. If it's convergent, it's absolutely convergent. If it's divergent, you go back to your series and you try to use the alternating series test to prove that your series is going to be convergent, and that give you conditionally convergent right at the beginning. Okay, so that was the case 2, and the case 3 is the one that we did. Okay, so the case 3 is exactly, you know, the way you have it on the quiz that I posted for you. It's 3 cases that you have to check. You see, this is n plus 1 and 5n plus 1. So for this one, again, it's alternating. If you put the absolute value around it, you are not going to get anywhere. Because that gives n over 5n. If you shrink it, that gives a fifth. So this means you see the limit of the general term, n plus 1 over 5n plus 1 that limit is a fifth, it's not zero. So this series is divergent right away. Okay, so don't miss it for this case. You see this is the one. It's a 1, 5, 1/5. So we say that the limit of, because basically, you know that if the limit of the general term is not going to be zero, that series is divergent. So the series, okay, so the series diverges. Okay, so that would be case, 3 cases that we're going to have. 1, 2, 3. For this type of problem, you have the part F is interesting. I do the F2 because this is a round. You see, look at the part F. It's a cosine of n pi over radical n. That cosine of the n pi, we already talked about it, and it usually comes in this type of series. If you remember, I've already talked about it. You see, when n equal to 1, cosine of the pi would be in -1. When n equal to 2, cosine of the 2 pi would be positive 1. N equal to 3, -1, positive 1, -1, 2. So you have to note that, you see, note that you can replace the cosine of the n pi by -1 to the n, because it's going to be +1, -1, +1, -1. So your series is in fact what? So the cosine of the n pi over radical n is the same as the sigma of -1 to the n over radical n. You see, this is your series. And we already talked about it. Is the alternating series. It's convergent, but it's not conditionally convergent. See, you check for the conditionally convergent, it's -1 to the n. I did it. You see, that gives a sigma of 1 over radical n, which is a sigma of 1 over n to the half. It's divergent. Divergent P series is a divergent P series with what? With P equal to the half, which is less than 1. So this means the given series is not absolutely convergent. The given series is not absolutely convergent. Absolutely convergent. Okay, you put the absolute value around it, it's happened to be bad luck. You get the divergent series. So this means you have to go back because they ask for the conditional convergent. So you have to go back to see if the original one is convergent. Of course, it's alternating series. Alternating series, Bn 1 over radical n, decreasing, limit 0. You say, oh, bet. Sigma of -1 to the n over radical n is an alternating series. Alternating series. Alternating series with what? With Bn equal to the 1 over radical n. And the limit of the Bn, you see the limit of the Bn, n goes to infinity, is the limit of 1 over radical n, n goes to infinity is 0, because we get a fixed numbers on the top, infinity on the bottom. And this is decreasing because n is getting bigger and bigger, the denominator is getting smaller and smaller, and the fraction getting smaller and smaller. So the Bn is decreasing, going down. So the series convergent. So the series converges. The series called ternary series converges. So the conclusion is that the absolute value is divergent. Series convergent, so the series is conditionally convergent. So the conclusion is going to be sigma of -1 to the n over radical n is conditionally convergent. And with that, so this is the way, we check these